this lecture, we're going to be covering the third module in the introduction chapter. Basically, we're going to be talking about break-even analysis, and we're going to be looking at how we can solve various types of models and equations using Newton's method and other root finding techniques. So basically, it's the goal of this module to provide an introduction to root finding software, break-even analysis, and show how optimization techniques can be incorporated and solved in complex break-even models. So many spreadsheet programs, including OpenOffice, have built-in root finding algorithms. So as you probably know at this point in the course, we're going to be using spreadsheet software. So we have a couple of options. The textbook that we are using talks about OpenOffice. If you don't know anything about OpenOffice, OpenOffice is basically um, it is a type of spreadsheet. Well, actually, it's an open suite. So basically, it's very similar to Microsoft Excel, Word, and PowerPoint. And the program that I use, which is a variant of OpenOffice, it's basically the exact same thing as OpenOffice. It just has a couple of other features, is called LibreOffice. And it's completely free. Just type in LibreOffice in a search engine, and it'll bring up the place for you to download it. And as you can see, this software basically is nearly identical to Excel, Microsoft Excel. So it would take these two cells and say do something like this cell plus this cell will equal this cell. So anytime I change one of these, you can see how it's going to update. And the textbook that we use is an open textbook that I've worked on for a few years, and I wrote it such that you could learn the material without having to buy software. And the software I decided to choose was LibreOffice or OpenOffice, and you can use that and step-by-step instructions of how to solve those different types of models. So I will be talking about this. To be honest with you, since that time, when I was using this software, it had some options in it that Microsoft Excel did not have. Since then, the market has changed, and Microsoft opened up their software a little more compared to what it used to be. There's free options, and this had to do with in large part the open source community, companies like Google and Dropbox providing free productivity software. So because of that, now I pretty much use Microsoft Excel. So anything that I teach you in OpenOffice or anything that's covered in the book using OpenOffice, you can use Microsoft Excel. And pretty much everyone now has a copy of this either through work or if you're a student, most institutions will actually provide you a license to for free software. So we're going to be doing everything in Microsoft Excel. I may jump back and forth just to show you how you can do it, solve these models in using other software, but for the most part, let's just plan on using Microsoft Excel. So when I talk about root finding algorithms, what do I mean? Well, some of you may or may not know what root finding algorithms are. If you don't know, you will know by the end of the lecture. These algorithms usually employ what's referred to as Newton's method to converge on the roots of a model. Newton's method was developed by Isaac Newton, so that was several hundred years ago, and it's still one of the most powerful root finding algorithms that we have. If you get to looking at software that employs root finding algorithms, unless it's very, very sophisticated, usually the default is Newton's method. So it's very powerful. I'm going to explain exactly how it works. Many of these algorithms do not have the ability to identify multiple roots, and the solutions are highly dependent on the initial starting conditions or the initial guess. And this section will discuss how to use the root finding algorithm found in OpenOffice or LibreOffice or in Microsoft Excel. Okay, so just for a moment, let's suppose we're trying to find the root associated with this function here, which we talked about earlier. the natural log of x minus x squared plus 3. So basically what we're trying to figure out is where does this function equal 0. So when you talk about finding the root of a function, that's really what you're asking. You're saying where does this function actually equal 0. And we can go in and we can graph this. And so another piece of software that I use is called GraphCalc. Provided a link on the LMS. And or you can just type in GraphCalc, and it's free software, and it's just basically graphing calculator software. You could use you could use this software to graph, or you can use your graphing calculator if you wanted to. So what function are we looking at? We're looking at the natural log of x, which is going to be ln x minus x squared plus 3, I think it was. Let me make sure. Yeah, okay. And we just want to see, I'm going to zoom in, we want to see where this function crosses the x-axis. So if I just move my cursor, you see over here to the right how as this cursor position changes, it will give you the x and the y values. So if I just move, just kind of rough it, move my cursor, it looks like at about 1.9 the function is equal to 0, and if I move over here it looks at about like 0.05 the function is equal to 0. So I can go in here and I can actually use analysis, and I can go to axis intercepts, and I can say, alright, equation 1, the initial guess, and I'm just going to guess a value of say 0.1, and I hit solve, and boom, gives me the answer, 0.049991. So that means that this function crosses the x-axis at 0.04991. If I have another guess of maybe about 1.8 and solve, notice that now it converges on this solution, which is 1.909. Okay, so what technique does this software use to find it? Well, notice that if I go back up here under, where was it, 2D graph, analysis, axis intercepts, you notice what it says, initial guess. Okay, so when I say a guess, what you're doing is you're giving an estimate to where you think this function is going to cross the x-axis, and then this algorithm that you learned about in the previous module kind of kicks in, this iterative algorithm, and it converges, or sometimes it doesn't converge, but hopefully it does converge, and it gives you a numerical approximation to the answer. Okay, so as can be seen in the following figure, this function has two roots located near approximately 0.05 and 1.9. Because of this, two guesses have to be created in order to find both roots. However, it should be noted that depending on the function, guesses may not always converge on the closest root. In this example, we'll create two guesses, one at 0.1, another at 1.5. Okay, and when we do this, we got the answers that I showed you just a moment ago using GraphCalc. Okay, so how do we do this in Excel? All right, well, the first thing that we're going to do is we're going to have the function. So these are just labels that I have placed in Excel. They don't really do anything. This value right here is our independent variable. So I can put in whatever number that I want. Let's suppose I put in 0.1. And this is the actual function. So notice that I'm taking the natural log of b2, which is x, minus b2 squared, which is x squared, plus 3. So whatever value I put in here, this is the cell that actually evaluates the value of the function. Okay? So we go back here and it says we're going to set initial guess at 0.1. So I'm going to come here and put in a value of 0.1. And you can see that this value here is not 0. So we're off. So I'm going to go up here under data, click on this data tab. I'm going to go to what if analysis, and I'm going to go to goal seek. and I'm going to say set cell. I'm going to set this cell, which is the actual function, to value of 0. I want it to be equal to 0 by changing this cell right here. And that's all you have to do. So something very similar, actually it's going to be nearly identical to what happens in GraphCalc is going to take place in Excel. I simply hit OK, and you can actually watch this iterate. So I'm going to hit OK and watch it. You see how you saw that change? It changed very, very quickly because I'm on a fast computer, and it says the target value is equal to 0. The current value is, this is essentially equal to 0. It's very close to 0. Negative 2 times 10 to the negative 5th power. So essentially this is equal to 0. Just with the number of digits I have, it just rounds off. But it's almost equal to 0, so we can see that this value is approximately 0.05. Then we're going to set another guess, and we're going to say, well, let's let this guess be 1.5. So I'm going to come here, set this to 1.5, do the exact same thing, what if analysis. Set this one. Unfortunately, you do have to do this over each time. And plug this value in, and hit OK, and it did the exact same thing. It just converged to another solution, which is a valid solution. So we see that this value is almost 1.9, 1.91, and it's essentially equal to 0 right here. Okay, so it found the two roots to this problem. So if we look, we see the values are about 0.05 and about 1.91, and we used Excel, or you could have done something nearly identical in OpenOffice or LibreOffice, and get the exact same answer. So I just wanted to show you how to use spreadsheet software to actually solve this. And I go through here and I show you basically how you would do this in OpenOffice. You would also go to GoalSeek, and then you would set your formula cell, your target value, your variable cell, have a guess in, and hit OK, and it converged on 0.05 and 1.9. So that's how you would solve this using OpenOffice or LibreOffice. But like I said, we're going to be using Excel, and that's all there is to it. So the use of computer software to solve for roots and optima will be discussed at great length throughout this text. Many spreadsheet programs, mathematical solving tools such as MATLAB and Mathematica, and even advanced graphing calculators. If you have say a TI-89 or a TI maybe an 85 or 86 or TI-92, one of the latest graphing calculators, usually they have some type of root finding software that is essentially Newton's method, and they employ these root finding algorithms that can be used to optimize models that will be discussed, like I said, throughout the course of this text. So in this example, we're going to examine how classical optimization techniques along with numerical analysis can be used to determine break-even points. But first, let's step back just a moment. Why are we even discussing this? Well, sometimes you're going to come across problems that you can't find closed form solutions to. So, throughout your student career, you have probably come across, many problems that look something like this. And you say, all right, how do you solve this? Well, you factor it out. This is going to be what? X plus 2 times x plus 3 is equal to 0, and then you say x plus 2 is equal to 0, so then x is going to equal negative 2, x plus 3 is equal to 0, x is equal to negative 3, ugly 3, so let me see if I can do a little bit better job on that. And here are the two roots, okay? So most problems that you have done so far have a closed form solution. So even if you have, something that say is x is equal to, say 1 plus the square root of 5 over 2, this is still a closed form solution. You can actually go in and you can actually, plug this into the calculator and get an answer. But what happens if you have, say, a problem that looks like this? X to the x power is equal to, uh, I don't know, say 20. What is the value of x? Just think about that just for a moment. How would you go about solving this? Well, you come in and start guessing. So you could say, well, 2 squared is equal to 4. 3 cubed is equal to 27. So maybe 2.5 raised to the 2.5 power is equal to what? Well, we can go in and we can actually figure that out. So I'll bring up the calculator and do something like 2.5 raised to, let me clear this out, 2.5 raised to the 2.5 power. So that's not it. 9.88. So how about maybe 2.7 raised to the 2.7 power? No, maybe 2.8 raised to the 2.8 power. Getting close. So you see what I'm doing. I'm guessing here. But I could go in and use, say, GraphCalc and do something like this. I could go in and say x raised to the x power, and graph that, and then put in something like 20 and graph that. I have to move up a little bit. Let me see if I can, there we go, I'll zoom out. And we can see that the answer is about 2.87 maybe. But I can go in and I can, get a pretty good approximation. I'm going to go intersection of two equations. Here are my two equations. My guess is going to be, let's say I plug in 2.7, I solve, and it says 2.855 is the answer I'm looking for. So I come down here and say 2.855 raised to the 2.855. And sure enough, that's pretty close, 19.87, and I could go out more digits and get closer approximation. So this is very important that we learn about this, because many, if not most, if not nearly all, real-world models that have any complexity about them, I'm not going to say it's impossible to get a closed form solution, but you run into this sort of thing a lot. Where finding a closed form solution is just very hard to do. And in the real world, we don't really care about closed form solutions. We care about something like, 2, 3, or 4 digits precision. So if you get some complicated model, even if there is a closed form solution, it may be very difficult to find. And then once you do find it, if all you're doing is just converting it to a decimal format anyway, then was it really worth it? In some cases it may be. It just depends on what field. But in the real world, when you're dealing with a lot of times money, or you're dealing with number of products, or where to turn a knob, it doesn't really matter. So we find ourselves using computers more and more and more, and Newton's method comes up a lot when it comes into solving hard problems. So because of that, we're going to rely on using software a lot in this class. Basically, this class is a class about building models. We're going to understand how to solve them, but then we say, okay, we're just going to let the computer do the work for us. So with that said, let's go here to Excel just real quick, and let's see if we can, well, let's go to OpenOffice. Since we haven't done OpenOffice yet, we haven't used it, let's just go in and try it. So say x raised to the x, 20. So I'm going to say this, I'm going to put a value here of like 2.5, and and I'm going to say equal this value raised to this value. And there's the answer. So you can see as I change this lower cell, the upper cell changes. Very, very simple what's going on here. So I'm going to go here under, I think it's, is it data? Let's see, tools. It's under tools, I think. Yeah, goal seek. I'm going to click on formula cell, which is this cell. Target value, we're going to say is equal to, and I can either put in, let's see, B2. So actually we're going to put in, I guess I could put in this cell. Does it? No, I actually have to put in the number. So I'm going to have to put in 20, and then my variable cell is going to be this cell right here. And so when I hit OK, watch what happens. Goal seek succeeded, insert yes, and it did the exact same thing that Excel did. It's just using different software, and this software happens to be free. So the answer is 2.855, which we confirmed using GraphCalc. So I just want to expose you to another tool that you can use to solve equations or models or whatever it may be. That's going to give you the answer in decimal form, but that may be okay. Okay, and for our purposes for the class, it is going to be okay. All right, so let's go in then, and let me see if I can find find this chapter real quick. This is the first chapter. I call it chapter IN because I wrote the book to be able, you can mix and match it, so each chapter is self-contained. So we're going to go down here, and I talk a lot about this and show you exactly how to solve all of these different types of problems using Newton's method and using the secant method, and then even how to use OpenOffice to solve this. Let's go in and let's take a look at an example. All right, so the example we're going to be looking at is, we're going to do, like I said, break-even analysis. So let's suppose a company is interested in selling polo shirts. They've hired a marketing firm and found that they can sell a maximum of 16,000 shirts a month. Okay. However, the firm has also established a relationship between the number of shirts sold and the selling price. So this is a pretty intuitive relationship. The numbers aren't intuitive. They are what they are, which you would get from a marketing firm. But basically what it means is, the higher you sell something for, the less of them you sell, which in general is true. There are probably, a few exceptions based on marketing where you buy designer products and that sort of thing. But in general, the more something costs, the fewer of them you actually sell. So let's suppose that this marketing firm has come back to us and they say the relationship between volume and price is this function, that you start off selling 16,000, and for every dollar you increase the price, you lose 400 sales. So if the item costs $1, you're going to sell 15,800. If it costs $20, 20 times 400 is 8,000. You're going to sell 8,000 of them. All right. So let's just assume that we have been given this number. Now, in the real world, you have to, or given this relationship, in the real world, you have to get this on your own. How do you do it? Well, that is complicated. You may have to do some research. You may have to do some regression fitting. You may have to go out and just, look at some historical data. But we're not going to be concerned with that right now. Okay? So here's the following graph shows the linear relationship between volume and price. The higher you sell something for, the less of them you sell. Now, this model is probably not completely accurate across the whole price range. So in reality, if you were only selling this for $1, you could still probably sell all 16,000 of them. If you were selling them for $2, you could still probably sell all 16,000 of them. So maybe it's not this nice, neat, linear relationship over the whole model, but in reality, you're probably not going to be selling these down at the low end for $1 or $2 or whatever it may be. So as long as it's valid or reasonably valid in a reasonable price frame, you're probably okay. Uh, this model could be as complicated as you want it to be. It doesn't have to be linear. You could come up with some quadratic model or logarithmic model or whatever it may be. Um, Maybe a little more difficult to develop the equations for, but we're going to learn later in the course that actually it probably wouldn't be that bad if you just plug these into some much larger model or plug it into a spreadsheet or whatever it may be. But with all that said, let's just assume we have a linear model just to give us some jumping off point, and then throughout the course you can make these as complex as your heart desires. Okay, so suppose the company analyzes their data and they determine that the cost to produce each shirt requires a $6 investment in material, labor, etc. Okay, so each shirt that you produce requires $6 worth of resources: time, labor, cloth, sewing, whatever it may be. Also, the fixed cost per month to maintain the machines, pay for utilities, uh, it's $12,000 a month. Therefore, the variable and fixed cost are, well, our variable cost, which is our price per item, is $6. All right, so if you make one item, it costs you $6. If you make two, it costs 12. If you make three, it costs 18, and so on and so forth. But you're paying $12,000 a month just to keep the doors of the factory open. Okay, so that's what's referred to as a fixed cost. And like I said, a variable cost is variable. It's dependent upon how many products you actually produce. So therefore, the revenue for the company per month is going to be revenue, which is your volume times your price. So it is how many you sell times how much you sell them for. So if you have, if you sell 100 items and you sell them for $10 a piece, your revenue is $1,000, 10 times 100. And the profit we're going to denote as Z, because in this course we usually denote our objective function as Z. So profit is simply going to be equal to Z, which is going to be revenue minus cost. So our revenue is our volume times our price, which is simple enough. That's the total amount of money coming in, minus our cost. What cost? Well, we have two costs. We have our fixed cost minus our variable cost. So the question the company needs to answer is, how much should we sell our polo shirts for? Well, before we go any further, we need to answer, what is our objective function? So many times a company, they'll try to say maximize revenue. You may think, well, the more money we're bringing in, the better off we are. So let's let revenue be our objective function and try to minimize this variable. So the relationship between revenue and price is as follows: V times P. Volume is 16,000, the quantity 16,000 minus 400P times P, or this function here, 16,000 times P minus 400P squared. So you immediately should recognize that this is a quadratic function right here, and so it's going to have two roots. So what are the roots to this? Well, you can go in and you can actually solve this, or we can look at it. And you could say, well, if P is equal to 0, 16,000 times 0 minus 400 times 0 squared is 0. So a root looks like it's going to be at 0, which it is. And then over here it looks like this is going to be 40. So 16,000 times 40 is what? 640,000 minus 400 times 40 squared. 40 squared is 1600 times 400 is 640,000. So 640,000 minus 640,000 is going to be 0. So just by inspection, we can see that this function right here has two roots, 0 and 40. All right. But let's do this the right way. Okay. So we see, okay, and so I skipped something. I said let's try to maximize this variable. So we're not necessarily looking where the revenue is equal to 0. We're looking where it is maximized. But by inspection, we can see that halfway between 0 and 40, it looks like 20, and it looks like it's maximized at 20. So let's just say 20, just do visual inspection. But now let's go in and do it the right way. How would we do it the right way? Well, the way we'll do it is you take the first derivative of the function. So the first derivative of 16,000 times p with respect to p is 16,000 minus 400 times p squared. So pull this 2 out. So we have 2 times 400 times p. And so the first derivative of this function gives 16,000 minus 800. This should say 800p right here. I left out the p, but let's assume there's a p right here. Solving for p yields 16,000 equals to 800p. P is equal to 20. So this means the company is going to make $160,000 in revenue by setting the price to $20. That looks to be about right through visual inspection. So just remember, taking the first derivative of a function tells you the slope of that function. We're trying to figure out where this slope is equal to 0, and that's going to give us a value of 20. Okay, so we solve this using traditional methods, using calculus and first derivatives and that sort of thing. Okay, so it's a classical calculus problem. So after analyzing the results, the question should be, did we choose the right objective? So we know that we maximized our revenue, but is that what we should be doing? Well, at first glance, this might seem like a reasonable objective. However, further inspection shows this may not be the right one. Are companies more interested in maximizing revenue or maximizing profit? The following equation shows profit as a function of price. So what would you rather do? Would you rather maximize your revenue, or would you rather maximize your profit? Because you can, in theory, have a revenue that is a high number or a low number. But if you think about it, you can have a revenue that's pretty high, but your profit be equal to 0. Think about it. If what is coming in equals what's going out, so if you have a revenue of $3 million a year, but your cost is $3 million a year, you're successfully making nothing. Okay? So is that what companies want to do? A lot of times the answer is no. They want to maximize their profit. So what is the equation for profit going to be? Well, it's going to be our revenue, which is this function right here, minus our cost, which is going to be 12,000, because that is our fixed cost. Okay, and let me see if I can write this. So remember, this value right here is VP, which is our revenue. This is our fixed cost, and this is minus our, what I'm going to say, total variable cost. Okay, because our variable cost is actually $6 per item, but this is actually our volume. So 6 is if you make 1, but your total variable cost is going to be the 6 times your total volume right here. Okay, and when you simplify this, it's going to yield this equation right here. So it's pretty close to what we had before. I mean, it's reasonably close, it seems. Okay, but it's a little different. So if we plug in 20 into this equation, plug in 20 here, 20 here, and we just run through and do the math. Let's get your calculator out and plug this in. You're going to get $100,000. Is that good or bad? I don't know. It is what it is. It's $100,000 in profit. All right. So we take the first derivative. This is our profit at 20, but we want to maximize this. Let's try to maximize. Okay. How do we do that? Well, the way we do it is we take the first derivative of the function and get this. So where does that come from? Well, we get negative 800p here, which is this guy right here, because this comes over here, this 2, and then this becomes a 1, so that gives us negative 800p. We get 18,400 because this guy drops out, and because this is a constant, when you take the first derivative of a constant, you get 0. So the first derivative of z is this guy right here. Okay? So if we go in and we solve for that equation, we get what? You get 18,400 divided by 800. So that's going to be, well, you're going to get 20, because 20 times 800 gives 16,000. 18,400 minus 16,000 is 2,400. 800 goes into 2,400 3 times. So just plug it into your calculator if you don't believe me. So this is saying that if we want to maximize revenue, we should set our price at $23. But that's different than 20. Why is it different? Well, the reason why it's different is because in one case we are maximizing revenue and in another case we are maximizing profit. Okay, so this is our profit at 23, $1,306. This is our profit at 20. So therefore it can be concluded that perhaps a price of $23 should be set instead of $20. Notice that the volume decreases from 8,000 to 6,800 when the price is changed from 20 to 23. So it's like, well, what are you talking about? Well, remember our volume is equal to, what do we say, 16,000 minus 400p. Yep, 16,000 times 400p. So this is going to be 400 times 23, and this gives us a number of 6,800, whereas the volume when it's set at 20 is equal to 8,000. So two things that happened here that we're going to discuss in just a minute is our profit went up and our volume went down. So let's just hold that thought. Let's take a look at these two curves. This is our revenue curve and this is our profit curve. So do you see how your profit curve is kind of skewed from your revenue curve? And obviously your profit and revenue is not going to be the same, but what is important is the location of these maximal points. So if you pick the wrong objective, do you see that if you picked revenue as your objective, but in reality you wanted profit to be your objective, that this is a suboptimal result? And just by picking the wrong value, you didn't maximize what your true profit could be. Okay? So it's pretty simple if you look at this, that if we go in here and we say, all right, well, how much did our profit increase? It increased 3.6%. How did I get that? Simple. 3,600 divided by 100,000. You have a difference of 3,600. 3,600 divided by 100,000 is going to yield 3.6% increase in profit, and all you did was just change your selling price. But more importantly, what I want you to notice is that to make $100,000 at a price of $20 a piece, you had to produce 8,000 shirts. If you increase that price to $23, your profit went up by $3,600 and you had to make now only 6,800 or 1,200 fewer shirts to make more money. So what would you do? Would you rather do more work and make less money, or do less work and make more money? So this is why OR is important, because what you're striving to do is make optimal decisions. So what I don't want you to do is to go back here and look at this, okay? Something like this, or to look at Newton's method and the secant method and to get frightened off and to say, oh, it's been a long time since I've done this, or you know what, it's been a while since I've really done one of these, and I can't quite remember what the derivatives are, and what did that do again, and oh, I'm kind of panicked. Don't do that. What I'm trying to get you to see is these are just simply tools that we're going to be using in this class, different software to help us get to the best answers. But this is what we're really after in this course. We're after making the absolute best decisions that we can based on the data that we have, and maximizing whatever objective it is that we're going to be trying to maximize, or sometimes you're trying to minimize an objective. Okay, so that's what I want you to get from this course. Is what I want you to do is I want you to look at this slide and say, wow, so all I had to do was increase my selling price by $3. That increased my profit by 3.6%, and it actually decreased the number of products that I had to make by, it's whatever 1,200 over 800 is. It'll be 12 over 80, which is 1,200 over 8,000, I'm sorry. 6 over 40, 3 over 20, 1.5. So it's going to be 1.5 over 10. So you could, is that right? 3 over 20, 1.5 over 10, which is going to be 15%. So, you reduce the number of items that you had to make by 15%, and your profit goes up 3.6%. And to many people, that's just unintuitive. That it's like, wait a minute, you mean to tell me I need to make fewer products? Yeah, that's right, because it's not that you want to be making fewer products, but by raising your price, it's going to be lowering your demand, but it's going to be offset because you increased a selling price from $20 up to $23. Okay, so that's what I want you to get. I want you just, not to get panicked of the math and say, oh, I get big picture. Big picture is that I'm making a decision that may be unintuitive, that is actually going to benefit me. Okay, so now we're going to take it to another level. Let's suppose that instead of just dealing with selling price, that management has decided to invest in advertising. Advertising in general increases sales. Okay, the marketing firm has indicated that increase in sales as a function of advertising is Y is going to be equal to 100% or 106 times the log of our advertising cost. Okay, why is this the case? Well, let's go back to the chapter and let's see if we have a graph that kind of gives us some intuition as to why this is the case. Well, we can kind of look at this, and this makes sense. If you think about this, advertising has what's referred to as a diminishing loss of return on investment. Okay, the more money you spend in advertising, the less return on investment you'll get. So spending a small amount of money will often yield a large increase, but then spending that same amount of money will not yield as much of an increase. Okay? And this is just one of those facts of life. And if you think about it, it kind of makes sense. Why does it make sense? Well, a lot of times this has to do with the fact that you have a finite population. Okay? So if you have, say, 100,000 people that are in your marketing area, think about what would be required to get all 100,000 people to buy your product. I mean, first of all, it would be nearly impossible. But if you did, think about the amount of energy it would take to let everyone know about this. Okay? So, how many people watch TV? Well, quite a few, but not everyone. How many people drive or ride on the roadways? Well, a lot, but not everyone. So you're going to have a certain number of people that it's going to be hard to let them know that you have the product. So you may have to put it in the newspaper. You may have to put it on television. You may have to put it on a billboard. You may have to go around and actually let people know door to door that you have this. So you could spend almost an infinite amount out here in advertising before you would actually get to where you're servicing everyone. So what happens is when you first start out, no one knows. If you're spending $0, no one knows that you have this product that you're trying to sell. But just a little bit of money, if it's a good deal, will let, a significant percentage of the population know about it. And then the more you spend, the more that you convince people that maybe they should buy your product. So that's why it follows this type of function. In reality, the way it probably really works is it follows probably more of an S shape, if you want to know the truth. But this is probably good enough. It's a pretty simple function. You're usually probably going to be spending past a certain threshold to where it's going to simulate a natural log. In theory, this guy doesn't really asymptote off. It ends up going to infinity, but it's pretty close. So this natural log function isn't a bad function. What I'm not really trying to sell exactly what it is that the function that we're actually using. Basically, like I said, I'm not trying to necessarily, justify this function and why we're using it. Just take it for what it is. This is the function that we're going to say describes advertising dollars compared to additional revenue generated. Okay, so just take it for what it is. You could use whatever function that actually fits your data, but this is the function we're going to be using in this example. Okay, so let's go through and see what our volume would be then. Okay, so our volume is this function, which I gave you earlier into the problem, which is probably still going to hold true, and we're going to add this amount. So now our volume is actually a function of two variables, price and advertising cost. So the new profit equation is going to be volume, which is just going to be this quantity. So even though it's kind of getting large, don't panic, because I could still just put in a V here to represent that. Volume times price. So this is just going to be revenue. Okay, so revenue is all of this right here, minus her fixed cost, which is 12,000, minus her total variable cost, which is still going to be 6, times this, which is just our volume. Okay, and then minus CA. Why do I minus the CA? Because I actually have to subtract the cost. So if you don't put this guy in here right here, what it'll do is just let CA go to infinity, because it says, oh, Well, there's an infinite return on investment and it doesn't cost me anything, so I'll just spend an infinite amount. So you have to make sure that you actually subtract your advertising cost out. And that's only logical because if you spend $10,000 in advertising, you actually spent $10,000 and it detracts from your profit. So if you go in and reduce all of this is just an algebra problem, you get this. Okay? So I'm not going to do it because I'm going to assume that you can multiply these out and add and subtract them, and this is what you get. Okay? So, how do we maximize this guy? Well, this is a little bit harder problem. Why? Because we have two independent variables. P, we got a P here, we got CA here, another CA here, another P. So we have to figure out what is the optimal value for P and C sub A. Alright, well, how do we do this? Well, the way we do this is you have to take the partial derivative with respect to P and with respect to advertising cost. Alright, so why is this the case? Well, essentially the reason why this is the case is because instead of this being a nice curve or surface now, this is actually like a surface, that looks like this. And you're trying to find where the optimal point is on that surface. So think about a basketball. Putting just a basketball down on the ground, on level ground, and where's the optimal point on that? Well, that's a sphere, so it'd be pretty easy to figure out. But imagine there is an optimal point on that surface, and it has an x and y coordinate and a z coordinate. This is exactly what we're doing with this problem. So what you're going to do is you're going to take the derivative of this big function right here with respect to P, and when you do that, you get this guy. And then you're going to take that derivative with respect to C sub A, and you get this guy right here. Alright? So, what do we have? Well, we're going to set both of those derivatives equal to 0. And if we didn't have this natural log guy in here, we might actually be able to solve for that. So you would have two equations and two unknown variables. And you would just solve for P, and you would solve for C sub A, and you'd be done with it. The problem is there's no easy way to separate these variables. So, because both decision variables are in each equation, the optimal solution cannot be determined independently. Both equations must be analyzed simultaneously. However, the solution methodology is quite simple. So what we're going to do is we're going to move this guy over here. Make sure that's how we did it. Yeah. And we're going to solve for P. So we're going to say P is equal to what? Well, we move this guy here, and then we multiply times C sub A, move this guy over here, and then divide out by 106. And when you do that, this is what you get. You get P as a function of C sub A. So P is equal to 636 plus C sub A divided by 106. So now what you can do is substitute in here, and wherever you see a P, you just substitute in this equation here. And when you do that, your P is right here, then you plug in this guy, then you multiply everything out, basically divide out by 2 here, divide out by 2 here, and you get 453, and you just multiply everything out, and this is the equation that you end up getting. And you have C sub A here twice. You want to set this guy equal to 0. And how do you do it? Well, good luck with that. C sub A is equal to what? Well, that's why we just went over Newton's method, because you can't solve this in a closed form solution. Okay, so what we're going to do is we're going to now go to Excel, and what what I have, let me just plug in a value here, is I have this equation. Oops. I have this equation right here. So if you look, 18,400 minus 400 times 336 plus B1 divided by 53, and you look at what is right here, what you'll find is that is this equation right here. Okay? The exact same equation. Make sure 400, yep, 53. So what I need to do then is, because this is a function of B1 and B1 is our advertising cost, I need to figure out what value I need to make this guy such that this one is equal to 0. Okay? Alright, well, let's get to work on it. I go to what if, goal seek. I say I want to set this cell equal to 0 by changing this cell. Hit OK, works, and boom. It says I should spend about $1,908. And this function, which is the first derivative we're trying to set equal to 0, becomes 0. So 1908, remember that. So I said let's put a starting value of 1,000. Find the approximate solution. This is how you would do it in OpenOffice. Get about 1908. And then, so that means I need to spend $1,908 on advertising. And then how much should I set my price? Before it was 23. Remember we had $23. Well, P, if you recall, is a function of advertising cost. So 636 plus 1908 divided by 106 gives approximately $24. So notice that our price went up. If you think about it, intuitively that makes sense. Why does it make sense? Because we are passing on the advertising cost that we incurred onto the customer. So essentially the difference between 23 to 24 is $1. Okay? So each customer is essentially paying $1 for you advertising to them. Alright? So what did this do for us? Well, if we plug in now what our profit is into this big equation that we created and plug in our new price and our new advertising cost, we find that our new profit is almost equal to 116,000. It's 115,705, but just for easy math, let's say 116,000. All right, so think about this. Our new profit is 116,000 or 115,705. So our profit went up 11%, 11.68% just by advertising. Okay? And remember that our advertising cost is already taken into account. So this approximately $2,000 that we spent, we've already included into our profit equation. So you don't have to go in and say, yeah, but of this extra 16,000 you have to deduct 2,000. No, it's already been built in. So I want you to think about this just a moment. If we chose the wrong objective, it was going to be, we were going to make $100,000 in profit. By choosing the right objective, this went to $103,600. By choosing the right objective and advertising at an optimal value, it went up to almost $116,000. So we increased our profit 11.68% by really doing nothing, just changing our decision. And this is the power of OR. that sometimes, many times it turns out, if you look at a process or you look at, decisions that are being made in a company based on, say, inventory or selling price or whatever it may be, you're probably not operating at an optimal value. And so we didn't really have to do anything. All we had to do was just change the price and do a little bit of advertising, and we got 11.68%, which is significant. Trust me. If you go into a company and you can increase their profit by 11.68%, any reasonable sized company, you're going to get recognized and you're probably going to get a pretty good bonus at the end of the year. So this is definitely worth it. So conducting research, building models, and spending months or years trying to increase productivity or profit by a few fraction of a percentage points make one wonder if it's worth it. So it's like, well, sometimes is it really worth it? Well, in the first years when OR was introduced into industry, you saw huge gains. Okay, because not everyone was doing it. After many years, it became more and more difficult to see a significant return on investment. But in a competitive market, many times the slightest advantage will make a lot of the difference as to whether a company will survive or not. So, your competitors, you don't have to undercut them by 11%. If you undercut them many times by 1%, in the long run, you're going to get more sales, because usually there's a nonlinear relationship between prices. Like, a perfect example is gas. Think about it. A lot of times you see gas stations right beside one another. Many times the prices are identical. Sometimes not. Sometimes, one brand will sell a little bit more than another because they say they have special additives or whatever, but really they're selling their brand, or maybe you've got a special card to buy that type of gas. Or I've also seen that sometimes with gas stations, and I find it absolutely amazing, that one gas station can sell their gas for a little bit more than another gas station. And you look and you say, how is that the case? Why wouldn't I just go pay 2 cents less? And then you really get to analyzing, say, the traffic patterns, and you see that, well, it's easier to get into this gas station versus this other gas station, or it has a little bit better lighting, or it looks cleaner, or it has new pavement, or whatever it may be. And you say, well, I'll just go to this gas station. What's 2 cents? And then when you really get to thinking about it and analyzing it, it's like, well, that 2 cents is actually exactly what they can charge based on where they're located or ease of access, and the market just kind of figures it out. But most of the time, there's actually a law in economics called the law of one price, that all things being equal, products will sell for the same price. And if they don't, then one product wins by an overwhelming majority, because it's just the way human minds work. So, because of a concept known as reinforcement or positive feedback, successes often build on themselves and the advantage becomes clear over time. So, in the example of adding advertisement to increase profit, only a modest increase was realized, basically about $12,000 a month or $144,000 a year. But think about that. That is a pretty good salary for a person. So take, say, $44,000 for insurance and benefits. So you could pay someone maybe $100,000 a year just by making the company more profitable. Okay? This increase can be used to perhaps hire 2 more marketing personnel or invest in some automation technology, which is actually going to make you more competitive, which is going to lower the prices even more. Each investment will make the company more and more competitive and therefore reduce or eliminate competition from other companies. And that's why, there's also in economics, it's called the law of threes, that basically you have 3 major companies in any particular industry. If you think about it, it holds true. Now, economies are always changing, so it's just the whole dynamic is pretty complex. But think about, for years you had Ford, GM, and Chrysler, Coca-Cola, Pepsi, and then whatever other third one to bring up the rear. And it happens over and over again. Microsoft, Apple, okay? Search engines, Google, basically the dominant. Android, Apple, and Microsoft is a phone operating system. So it's the way markets kind of drive that the better get better, they acquire more, they get bigger, and that's why this is so important. So a somewhat unrelated example that gives insight into this phenomenon is a simulation that I like to talk about. And let's take a quick look at this. You may have seen this before, but I always just like to show it because this really demonstrates what happens in a free market economy. So this is just an agent-based model. You don't have to know anything about any of the details. Let's see what we have here. Socials. Usually this is simple birth rates. That's what it's usually called. Let me see if I can. Maybe I've got it on recent. Let me see. Recent files. Yeah, I'll go to simple birth rates. There we go. And it's just two species that are competing with one another. You don't really have to know the details as to what's going on, but basically we have you have red agents and blue agents. They move around, they reproduce. The fertility of the blue agents is 2.1 children. The fertility of the red agents is 2 children. We start off with 500 of each. We have a carrying capacity of 1,000, which basically means once it gets over 1,000, they randomly die off. And we just want to see what the steady state of the proportion of reds to blues. So if you look at this, it's usually pretty easy to convince someone that the steady state ratio between blue to red is going to be about 2.1 to 2. Okay, so it's going to be a slight imbalance. Maybe you would think that you'll have 550 to 450, 550 blues to 450 reds, but when you run this, look what happens. Is time and time again that the reds die off and you're left with completely blues. So you can run it over and over and over again. And actually I'm going to do that. I'm just going to run the experiment and it's going to run it over and over. So when the reds finally die off, it'll restart and it'll come down here and it'll say, okay, red was extinct after 202 generations. Run it again. Red was extinct after 160 generations. So what this demonstrates is something that happens in biological systems, it happens in economic systems, it happens in almost everything, that this small competitive advantage builds on itself. So let's go in now and let's make this fertility, instead of 2.01 or 2.1, let's make it 2.01, which is the slightest competitive advantage. And look what happens. Well, it looks like the red is going to win, and sometimes it will, just through random variation. Sometimes that will actually happen. But in general, what you will see is most of the time that the blue, because it just has a very slight competitive advantage over the red, it will have a tendency to win. And we can see that looks like that's what's occurring at this point. And you see the reds slowly tending towards zero. Took a little bit longer, took about 918 generations that time for it to win. Looks like it's probably going to win a little bit quicker this go around, but we'll see. And so, like I said, don't get hung up on the details behind what's going on in this model. I don't expect you to know anything about NetLogo or agent-based models or anything like that. That would be another course. But what this does demonstrate is how competitive markets actually work. And it just, what I'm trying to show to you is that a slight competitive advantage will build over time and ultimately will cause your competition to go out of business. And we can speed this up. I can actually make this go much quicker if I want to. And it'll happen, faster and faster and faster. But all I'm trying to get you to see is just why OR is important and why a few percentage uh, increase in profits or revenue or whatever it may be is worth it. Okay. So research is not a luxury; it's actually a necessity when you get out in a competitive market. So throughout the course, we'll see how many algorithms are developed and implemented for the purpose of solving models. As can be expected, the power of the computer will be harnessed for the purpose of quickly implementing algorithms and using them to solve advanced OR models. So in practice, a large number of algorithms that will be discussed are already implemented in commercial and or open source software packages. So refer to any handouts, any homework, that sort of thing, and that basically will wrap up this module.